Yeah.
I heard Eva. I heard Sn1.
Sn1.
But that's just because,
Okay, well that's a terrible pen.
It does.
Let's try a better pen.
Yay!
Let's try this one. Yeah. So, last class we did Sn2 substitution reactions, and today we're going to pick up the next one in the series, Sn1. So, one of the classic ways to introduce Sn1 is if you were looking at this particular setup for a reaction following the Sn2 lecture, you would probably start assessing the quality of the nucleophile and the steric hindrance and think, well, here we have a poor nucleophile. We also have a polar protic solvent, which makes it an even worse nucleophile. And then we have this bulky T-butyl group, so we have steric hindrance. So everything together here, this should not proceed for a substitution reaction because all we've seen is Sn2 up until this point. But it turns out that this actually proceeds quite well. And what happens is you get a different type of substitution reaction. And the HBr is dissociated because it's just a salt in aqueous solution. So you can put aqueous in there if you wanted to. And this actually goes off like a shot. And the reason is because it's not an Sn2 reaction, it's an Sn1 reaction. So this has a completely different mechanism that isn't limited in the ways that Sn2 reactions are limited, but it has its own set of limitations and constraints and considerations that we have to account for when we're predicting the outcomes of the reactions. So let's see here. A couple things that are important to point out. In the Sn2 reaction, we had an effect where if you doubled the concentration of the alkyl halide, that would double your rate of reaction. Likewise, if you doubled the concentration of your nucleophile, that would double your rate of reaction. If you doubled both, you would quadruple the rate of reaction. So both the nucleophile and the alkyl halide acting as the electrophile mattered in terms of determining the rate for the reaction, which is why it was a bimolecular reaction. It was at Sn2. In this particular case, the concentration of the nucleophile doesn't matter. The only thing that matters in the rate determining step is the concentration of the alkyl halide. So that's going to be our first big clue that you have a big difference in mechanism. And that's why it's unimolecular, so substitution nucleophilic unimolecular in mechanism. Let's see. Other important points. Second big difference is before we had a nucleophile and then we had to pick a solvent, and our solvent needed to be polar and aprotic to be effective at hosting it as a nucleophile so it didn't quench it like these polar protic solvents do. In this case, for Sn1 reactions, the nucleophile is also solvent. So we're going to have a lot of nucleophile present in any particular reaction, a huge excess available. And so even though it's a relatively weak nucleophile, one, it's going to be highly motivated to react with this after the first step of the mechanism, and it's going to be so abundant that it's going to make it more probable for it to happen as well. So with these things kind of all in consideration now, let's just go ahead and walk through the mechanism and we'll see why it's different. Not gonna happen. So the first step in Sn1 is that bromine spontaneously leaves as a leaving group. And this is an equilibrium step that is not favored to products. It's favored towards the reactant with it being associated, but we do have an equilibrium condition, and it's slow. But what this results in is, in this case, a tertiary carbocation. Now, even though we have a really slow first step that's not favorable, the next step is highly favorable. And what that's going to do is consume this product and drag the equilibrium this direction towards products via Le Chatelier's principle. So even though this first step isn't favorable, because we're consuming this one so effectively in the next step, it goes really smoothly towards completion. So in the next step, if we're doing this with water, and we don't have to do this with water. We can use any polar protic solvent. We can use any of our alcohols. We can use methanol, ethanol, water. Any of these solvents that are polar protic can participate in the same fashion as water can. And instead of adding hydroxyl, we would be adding methyl ether or ethyl ether, something like that, equivalent. But for now, we'll just use water as our solvent and nucleophile. And we get a fast step where the water adds. And then we get a second step where our second equivalent of water comes in and grabs the proton, breaking this bond, pushing the electrons to this oxygen, and satisfies the positive charge. And so our product is going to be the T-butyl alcohol and the generation of a little bit of acid.
That little arrow on the double side.
Yes. Oh, this one? No.
No, because it's so favorable.
Yeah. And both of these steps are fast steps. And this is a very favorable to product equilibrium system. So this is a much more stable product than this. This will be highly favored. So you can think of these, basically this is our first step. Now here's the important thing. Because this is the rate determining step, reach that high. I'm not even going to spell the whole thing out because I can't reach that high. Because that's rate determining, the concentration of the nucleophile isn't a factor in determining the rate. Only the concentration of the alkyl halide matters because its normal dissociation is what's going to determine how fast the reaction can proceed. So this gives us a little bit of insight into limitations of this particular mechanism. For one, we need to have a alkyl halide that can spontaneously form some amount of a carbocation. So we need to have a stabilized carbocation. So primary and methyl are out of the question. They're not going to happen. Unlike Sn2, where those were our favorable alkyl halides for those reactions. Secondary, we'll walk through that in a little bit, but functionally, it's not favorable also. So really, what we're looking at are tertiary carbocations only, or tertiary alkyl halides for substrates for our Sn1s. Other considerations, stereochemistry. Oh, any questions before I move on to stereochemistry? Before I start erasing things? Okay. So for the Sn2, we had some nucleophile, and it had to attack from the back side of the carbon to drive the leaving group off. And we talked about the presence of the antibody orbital that resided directly behind, and that gave us a place to put these electrons as to form a new bond while breaking this bond. And as part of doing this, these three components get pushed into a trigonal bipyramidal structure as this bond forms and this bond starts to break. And then as this bond breaks, these continue to get pushed and what ends up happening is, as part of an Sn2 mechanism, you get inversion of the stereo center. So if you had a chiral center, the chiral center is going to get inverted as part of an Sn2 mechanism. We don't see this type of effect in the Sn1 mechanism. So when you're predicting the product, we're not going to be seeing this inversion of a stereo center. We're going to see something different. We're going to see partial racemization. So I guess I can leave that up. For this one, because let's say we'll go with the T-butyl because it's classic. When the bromine spontaneously leaves, we have only 3 groups remaining. And when you have 3 groups remaining, you have lost any potential for chirality. So even though this wasn't chiral, let's change it up. Let's pretend it was chiral. Okay, there. Now we have a chiral center. We have a methyl, ethyl, and propyl group around our tertiary carbon, and the bromine's going to pop off, and that's going to give us let's see here, CH3, CH2, CH2, CH3, CH2, CH3. There we go. So for our second step, our first fast step, the water can come in, and water as a nucleophile, because it's also the solvent, can attack from either side. And when that happens, yes?
If there's no lone pair there, why is there stereochemistry? Shouldn't it just be a planar?
It is. Sorry. The convention when I'm trying to show it tilted on side. So this is trigonal planar. And what I did is, instead of having these drawn wide, I tried to take it and flip it so this wedge is straight out and that wedge is straight back. So it is trigonal planar if you're viewing it straight on with close to 120 degree angles. And then I just took this and rotated at 90 degrees. So this, I had to separate them enough where I could draw in the groups. So. Okay. Yeah, so there is a loss of chirality at this point. And we can attack with the nucleophile from either side. So if you attack with the nucleophile on this side, all these groups are going to get pushed in this direction, and you're going to end up with a new chiral center with one type of chirality. And if you come in from this side, all these groups get pushed over this way, and you're going to have the opposite stereochemistry. So you're going to have, to some degree, a racemic product. Let me just go ahead and get rid of this. Get a little bit more room.
So, if you have the opposite curve, stereochemistry, the nucleophile attack from the backside, or does that even matter?
There is no backside.
Oh,
Yeah,
because it's planar. So here's the logistic, though. It's not going to be a perfect racemic mixture. Because what's going to happen is once this dissociates, the bromine's still kind of hanging out. So even though it's not bonded and there's a little bit of distance here, the opportunity for our nucleophile to attack from this side, which doesn't have the bromine occupying the space, is a little bit higher than the opportunity coming this way. So because the bromine is physically on this side, drawn away, attacking from this position is going to be slightly more favored than attacking from this position. So let's see here. What would be slightly favored would be attacking from here. So the methyl would get pushed over, this wedge, the propyl group. And this is after the second step as well, so we're just add the hydroxyl group. What did I do? There we go. That's better. And then this would be slightly favored. Over the opposite product, if we came in the other side, we could just draw this as the mirror image, and that would be the slightly less favored product.
Was the reason it's slightly favored because of this there strain again? Or?
No, it's just the opportunity for the nucleophile to participate in the reaction. Because this, once the bond breaks, is still here, so there's a little bit of this getting in the way of the solvent / nucleophile accessing the carbocation.
Go to the opposite, generally want to go to the opposite.
Right,
side.
because it's just the speed with which, so as this, let's say there's a water here. Oh, this is getting terrible. And there's a water here. Until this dissociates far enough away through diffusion, it's not going to be as accessible for the nucleophile to get the second attack here. So because it physically was here and we have to get a little bit of distance, it's just going to happen a little more slowly, and because of that, the one that can happen more readily is going to be favored, just through probability. Not because the product is more favorable or more stable, it's just the speed with which this can take place is slightly faster than the speed with which this can take place. Yeah?
Is it close enough that these are both considered major products?
Yes. Okay, so let's talk about factors which drive Sn1 substitution reactions. First off, you have to have a good leaving group. Come on. Okay. You gotta have a good leaving group. Because the first step involves putting electrons on the leaving group. So if the leaving group doesn't like to hold electrons, isn't fairly stable holding those electrons, it's not going to proceed spontaneously. You're not going to get a carbocation forming if there isn't some place for those electrons to go. So you have to have a quality leaving group. And the criteria for what makes a good leaving group for an Sn1 reaction is exactly the same as what made a good leaving group for the Sn2 reaction. So a good leaving group is a good leaving group regardless of whether it's Sn1 or Sn2. Quick review. Our alkyl iodide is going to be superior to our bromide, which will be superior to our chloride, which will be superior to our fluoride, with fluoride being our least reactive, and our iodide being our most reactive because it's a superior leaving group. It's easier to get those extra electrons onto the iodide because of its size and its relative basicity. see, other considerations. The other factor, so this is our first factor, quality leaving group. Second factor, we've already talked about this once, but we'll do it again, stability of our carbocation. So, functionally, if you want to have any reasonable rate of reaction or yield, you need to have tertiary carbocation to have an Sn1 mechanism. You can limp something along with a secondary, even though the book says you can't. You can. It's just, it's not a favorable reaction, and you should probably pick a different reaction that's going to do the same thing that you want in a better fashion. So tertiary is really where we need to be. Primary is completely out of the question. Methyl is completely out of the question. Now, one of the classic questions that really trips people up with this chapter isn't what we're about to do. We're about to set up that one later. But leading into, this is one of the easier questions that leads to the harder questions is, given a structure and a nucleophile and a solvent, would you expect to see an Sn1 mechanism or an Sn2 mechanism? And once you've predicted that, you have to predict the product with the correct stereochemistry or combination of products if it's a racemate. So first step is it Sn1 or Sn2 if you have a situation that's competitive. And let's see here. If it's primary or methyl alkyl halide, you're not spontaneously forming carbocation. So no carbocation means no Sn1, which is a long way to say Sn2 only. Now, in former years when I was even more mean than I am now, I would have trick questions where I would say, okay, well, we've got methyl iodide, and everyone's like, oh, dang, methyl iodide, that's a killer setup for an Sn2 in water. Does what? Nothing. Nothing. It's a terrible reaction. I know. I haven't done that in a while, but I haven't taught OChem in a while, so I don't know. It's a fair question though, because one of your you could say no reaction, or Dr. McGill did something weird here, because here we have a terrible nucleophile, and you're not going to get Sn2 substitution reaction without a decent nucleophile, and it's definitely not going to happen in a polar protic solvent with a terrible nucleophile. Yeah?
But when you have redissociation of H2O into hydroxide, which is a pretty good?
Still, it's so trivial. It's so trivial for the spontaneous dissociation, and it's still in a polar protic solvent, which is not going to be favorable for Sn2. So just because my point being, just because you have an alkyl halide doesn't mean a reaction will proceed. You still have to have the other, if you have this great methyl alkyl halide with this great leaving group, you still have to have a decent nucleophile, and you have to have a solvent which supports Sn2. So if it's tertiary, so this one's super easy. Tertiary, super easy because it's sterically hindered. So Sn2 can't proceed. Can't go. So Sn2 is out of the equation. So we're looking at Sn1 only. What about secondary? For substitution reactions, this is going to strongly favor Sn2 because this does not spontaneously form carbocations well enough to favor this mechanism. The rate of reaction is going to be super slow. Yeah, if you put this in water, eventually you're probably going to get a little bit of product forming, but it's going to be a very slow, favorable, non-favorable reaction. You're not going to do this in a laboratory for any reason intentionally. So set it up as an Sn2 if you have a secondary. You still have to have a good nucleophile. You still have to have a polar aprotic solvent. Now, what's going to make this more complex is we're going to start doing elimination reactions. And at the end of elimination reactions, we're going to have to decide, given a setup, whether or not something goes through an Sn2 or Sn1 reaction or an E2 or an E1 elimination. And that's going to be more nuanced than this. So this one is the fairly easy points. The one where you have to judge what's most likely to occur with all of them, or maybe a mixture of products, is the trickier one. And that's, like, got to have one of those on the test. You're not testing over substitution and elimination reactions if you don't have at least one of those on the exam. So just be prepared. So, any questions about anything so far before we go on to elimination? Okay, I was going to say, this is scary because when there's a class that usually asks questions and there's no questions, that usually means that there's a lot of questions that aren't getting asked. Yeah?
Oh, I was just going to ask, when you said E2 elimination, is that just redundant?
Yes.
Okay.
Because I haven't taught it, so like substitute. So it's like
Go.
elimination, bimolecular elimination. Yeah. Case. Yeah. It's redundant.
That's all I was doing.
Okay.
Yeah, that was the thing.
Okay.
I have a question.
Yes.
I'm sorry if I already missed it. If for a tertiary, Sn2 would be sterically hindered, why isn't Sn1 also sterically hindered? Or why is it less so than Sn2?
Sn1 doesn't have an initial attack. So for the Sn2 reaction, if you have something like a T-butyl iodide, and we have some nucleophile. This nucleophile is going to have a hard time accessing the backside attack of this tertiary carbon, because when we see it drawn like this, you see CH3, you think, oh, that's not that big, but
Draw it out.
each of these carbons has another bond, 3 bonds with hydrogens, and these really get in the way of accessing that attack. So you have a steric issue with the bimolecular reaction. With the Sn1, we don't need to worry about nucleophilic attack. We just need to worry about stabilizing the loss of these electrons and forming a carbocation, which in this case being tertiary favors, and there's no issue with these getting in the way of this leaving. see. Okay. Any other questions? Okay. So let's look at this primary alkyl halide. We've got a primary alkyl halide. We'll assume X is a good leaving group. We have some species Y, which I would normally call a nucleophile so far, but how it acts is technically going to depend on whether it's a substitution reaction or elimination reaction. The reason is because, oh my goodness, come on. We've been using this as a nucleophile. And I've been just saying generic nucleophile. But what is hydroxide classically? I think somebody whispered it. Base. Yep, it's both. What's the difference between an acid and a base? Still a fair question, not topically relevant. What's the difference between a nucleophile and a base? What's a base like to do?
A base accepts a proton.
Yes. A base accepts a proton because it likes to give its electrons to that proton. What's a nucleophile do? To an electrophile. So this likes to give its electron specifically to a proton, which is an electrophile, and this likes to do all of the electrophiles. So they're very, very, very similar. And Dr. Tomko was telling me a joke he tells at this stage, which I thought was super funny, is that this is kind of like when you get married, you get, you know, the spouse's family also. So when you're nucleophile, you get the base. When you are the base, you get the nucleophile. It seemed funny because my in-laws are awesome.
As you post this to YouTube.
They don't watch stuff like this. There's no chance of them ever like, huh, I'm going to randomly look up some low popularity organic chemistry. What?
Your family doesn't check up on your.
My family.
You might need to roll a crit hit.
Yeah. I'm, and if they do, there's no way they're going to this episode. My wife literally criticized the quality of my Biochem online videos, saying she could go to sleep if she really needed to go to sleep by just flipping on my Biochem videos. So, and she's the only one in her family with a college degree, and it's not in sciences, even though she got an A in chemistry. This is where you guys are like, were you a TA? Yes. But that's not how we met.
Oh, okay.
I was TA in a different class when we met.
Good. Good. Cover your bases there.
Yeah.
And nucleophile.
Where are we? Okay, so we've got a primary, primary alkyl halide, something that could be either a nucleophile or a base, which is why we kept it Y for now. And depending on what happens, oh my goodness, is there any chance of having, oh, maybe these are just hiding. Are these good? Oh yeah. Somebody stash them. Look at that. It's the little things. It's the little things.
You could also save the blue one that's on the board if you close the tab.
What?
There's
No, there's no saving that. Substitution. So if we do a substitution reaction, the Y goes in for the X leaves. In this particular case, it would have to be what? Sn1 or Sn2 because of the structure.
Sn2.
It'd have to be Sn2. Would you have to worry about the chirality after that Sn2 reaction? Because say chiral, because we've got two identical groups on the carbon, so it's achiral to begin with. So if we do an elimination style reaction, what's going to happen is we're going to get rid of the X, and we're going to get rid of one of these hydrogens, and we're going to form a double bond. So if I were to draw this out, X is going to go, and we're going to lose one of our protons. In this case, it's going to be the more substituted. It could be either of these. And we're going to get the formation of a double bond between those two groups. So this brings us to the E2 reaction, which is our elimination bimolecular. So funny because, like, you know how low my view count is on these videos? I've had videos up for a month that have 7 views. My students won't even watch my video. There's no chance. I have a higher chance of winning the Alaska lottery that doesn't exist.
How many online class?
Huh?
More than 7. Dr. McGill?
30.
Oh.
Yeah, exactly.
I mean, how many of them just come in here? So.
Yeah.
You said that,
I don't know anybody. I just like kind of pretend to acknowledge people in the group as I sway side to side and talk. Yeah.
You said it's the X and there's multiple hydrogens it could leave.
We're going to talk about which go in a moment. We will be addressing that question in gruesome detail.
Oh no.
Yeah. Yeah. So, let's see here. Let's just go, I'll just erase this as an option for now. Let's say, do a specific example. Looking at this, previously you would think, this certainly looks like the setup for an Sn1. But what we're going to look at is this also can do elimination. Oh man, this is one of those fun things where it's like, man, it can be Sn1 or it can be E2. And we'll have to get to those details once we're finished with all the variables. So how does this occur mechanistically? And why is it bimolecular? Because before, when we were just doing Sn1, this spontaneously fell off and it was unimolecular. Well, let's see here. In this particular case, the hydroxide is going to act as a base for this example, instead of as a nucleophile. And nucleophiles, remember, attack something specifically in terms of donating its electrons. in this case, we're getting something similar, but we're going to abstract one of the protons. And when we abstract this proton, the bonding electrons between that proton and the carbon can't stay bound because we can't exceed the duet on this hydrogen. So these electrons are going to pop to between the carbons, forming a double bond. That's going to exceed the octet on those carbons. So because we have a great leaving group here, we can break that bond and push those electrons to the bromine, giving us a bromide. And that is the entire mechanism. For the reaction. So super simple mechanism. This is also called dehydrohalogenation. And it's also called beta elimination. So the reason it's called beta elimination is because this is our alpha carbon, it's the central carbon, which has the alkyl halide, the halide bound to it as the alkyl halide, and this is our beta carbon. This is also, and that is also our beta carbon. So you might notice one of the reasons that this has a high chance of happening is because we can take this hydrogen, or this hydrogen, or any of these three hydrogens, or any of these three hydrogens because they're all equivalent. So there's lots of opportunity for this to act as a base on any of these positions. And it gives you the same product regardless of which of these hydrogens gets abstracted by the base. So because we are doing a basic attack on a hydrogen bound to our beta carbon, that's why it's also referred to as beta elimination. We have, who's first?
Just because of the unique situation here, is it correct to draw that bond between the hydrogen and the carbon to the bond between the alpha and the beta carbon, or should it be drawn to the beta carbon?
Because the electrons are being shared between here and here, if I was to do something and move this all the way over to the carbon, that would imply that I might be having a hydride transfer of some kind, some other groups moving. I think because we're sharing these electrons now, instead of between here and here, to between here and here, that's a better way to show it.
Never mind, okay.
Yes.
Why couldn't you form a carbocation and then have like a methyl shift?
A methyl shift?
Hydride.
More substituted carbons to have any H groups to do a hydride shift?
Because it isn't
What's going to shift? There's no room for anything to shift. Once you form the if you were to form the carbocation, if you were to shift any of these protons, the carbocation is already tertiary, and these are all primary. So if you're to do a hydride shift, you then try to be shifting to a primary carbocation, which isn't favorable. And there's no rationale for shifting from a tertiary to a tertiary. It only works if you're improving from a secondary or primary to a tertiary.
No, I think he's asking why it results in that carbocation. That's what he's.
Results in
Is where if you just
what
keep it going
carbocation?
with the CH2
The
on
one
the
that
left would end up with a positive charge, which would then shift over to the central carbon. Right.
No, so he was imagining if you took off that double bond and put that plus next to the alpha carbon, that was the carbocation. He was wondering.
So then we're going back to Sn1 mechanisms where this just falls off and you have a carbocation, which is a different mechanism.
I think we were wondering like how to discriminate when you're looking at the reactants.
Oh, we'll get there.
Okay.
We'll get there. Discrimination doesn't happen right away. We have to, we haven't even seen all of the elimination reactions yet. You guys skip ahead in videos, don't you? You're like, who's the killer? Okay, go back, watch the movie.
I mean,
Times 2 speed.
Yeah.
Times 2 speed? That's how everybody watches my videos, it turns out. I don't even know where I am anymore. Oh, here we go. Okay.
Elimination.
Elimination. We're still on elimination. Okay, so, wait. Are there any other questions before I erase stuff that I can't answer until we get through elimination?
Just keep going, otherwise.
Just
we'll-
keep going? Okay.
Yeah.
We'll just keep going.
Just keep going, otherwise we'll ask questions that we don't want to ask.
One of my favorite, we interviewed this guy for a professor job years ago. He was not given the job.
Oh.
He had an amazing lecture. And he was really engaging. And one of the students, and he looked at the audience at some point, he was behind, said, "Any questions? Good, thanks." And just kept
That is dope.
he had a good sense of humor about it. So, right, of course, there's going to be regioselectivity, right? Because we've already got stereoselectivity and we've got regioselectivity, so we've got to keep making things a little bit more real. So let's take a look at a secondary example. And we'll use methoxide, which is just the methanol equivalent of hydroxide as our base in this time. And for this to take place, we are going to come in and we're going to pull off this proton, or proton from here, or proton from here, and lose the bromine as part of our elimination reaction, and we can form a double bond here or here. Because this is symmetric, if we form the bond here or here, we get the same product. It doesn't matter.
Sort of the resonance
Not a resonance structure. It's not going back and forth. So, because it's not.
It's one
It picks one and it rolls with it. It doesn't-
Yeah, exactly. So it
Not
doesn't.
jumping between.
If this is eliminated, you get this product. If this is eliminated, you
Still
get this product.
Okay.
So because you have
It's symmetric.
either of these can be taken, but because it's symmetric around the point that either can be taken, you get the same product. Now, if you have this, you have the ability to form two different products. We'll call this A, B. If we eliminate at position A, we get this. If we eliminate at position B, we get this. Now, one of these is more favored over the other. And it turns out that this one is about 80% preferred. This one's only 20%.
Just because it's more stabilized than Jen.
It's not necessary. It's close. Close. The rationale is almost identical. So factors which stabilize an alkene are also going to stabilize the transition state. So it's the same general set of rationales. Because as we're breaking one bond and forming this bond as part of the mechanism, as it starts to form in the transition state that's most stabilized is going to proceed more quickly. And so the transition state that has double bond character that's more supported, which is the more substituted one, is preferred. So it's not because the product is more stable, it's because the transition state, which is similar to the product, is more stable. But the very, very close though.
So more stable transition state.
Mm-hmm. And the rationale is that because as the transition state is forming that double bond, the one that has that double bond character that's more supported because of the degree of substitution is going to have a lower energetic barrier and will proceed more quickly. So
A is the major product.
A is our 80% product. Yeah.
If this was a question, is it because it's 80-20, would we have to mention B as a major? No.
You probably draw both and point to the one that's preferred because they're not always. So this is a. Here, let's see here. We've got. There's this interesting rule called Zaitsev's rule, which talks exclusively about which one's preferred based on the number of hydrogens around the place where it's taken. And it says that the hydrogen is taken from the carbon which has the fewest hydrogens to begin with. But they specifically refer to the number of hydrogens as Zaitsev's, but I always think about substitution as the most carbons. So in this case, we'd be pulling the hydrogen from here because it's going to result in the more substituted product versus pulling it from here because then we'll end up with a less substituted product. But you can always just look at the degree of carbon substitution and say, okay, this is going to be our more stabilized transition state because it's the more stabilized alkene. Now, the thing is, that doesn't always hold true. It holds true most of the time, but there's a couple scenarios in which you don't see this pattern, where the more substituted product is preferred. So let's take a look at some of those exceptions. Excuse me. Okay, so first, if you have a bulky base, think about what a large base would do mechanistically here. If you've got this as our tertiary alkyl halide, and we come in with T-butoxide. As our base. I don't think I've ever, and that might be the first time in my career that's actually worked.
You got it on video, so.
Except nobody believed, like, just all they hear on videos, ooh. Which probably means I was like, did he just hit a student with that? When I was in 7th grade, there was a nun who threw everything.
Ooh.
She wasn't fast, but she had a pretty wicked arm. But she couldn't aim. She never hit anybody she intended to. So if somebody was misbehaving near you, you had to like, stop it, because Sister Patricia was about to wing something right at you, inadvertently. Garbage cans, chairs, didn't matter. Like, seriously, she would take a whole garbage can with half full of garbage and just...
This doesn't sound real.
Have you ever been to
Yeah, I believe it.
Yeah.
This was Catholic school in 1991.
Yeah.
Things were different.
We still can run that way.
Are you sure it was the 50s?
Protestant
Huh?
fancy.
Yeah. I'm not Catholic. I was just going to school.
That's why she's fancy.
It was a great time to come out as an atheist. Father Pepin, we had some good discussions about it. He made me debate the opposite position in religion class. We had a question, not regarding my history of nuns throwing things at me. Do we have a question? No? Okay. This is also on YouTube. So all of my stories of lab accidents and traumatic nuns are on YouTube.
No, they come from a part where it's like true to you.
Well, you know, it gets everybody re-involved in the class. It humanizes me and makes me look less mechanical. So, like we were saying, we have these options to take. I'm not going to look at this one because it's equivalent of this one. However, for the sake of when we look at the ratios, remember that that was also an opportunity, and so this and this have the same degree of opportunity. So when we look at the percent yield of one product versus another, remember that as high as this one is, it actually has half the reactivity per site available to it.
Wait, can you say that?
So whatever percent you get, it's really half. Of
Right. So since you guys like spoilers,
Yes. Throw it.
Yeah,
Super
super
two, make it a second time.
oh. No!
Come on.
That was a 3-pointer. That was all the points. Good. So, oh yeah, spoilers. Based on what we had just discussed with Zaitsev's rule, you would expect elimination at this position to be favored. However, that's only 28% favored.
Is there a way to quantify bulkiness, or do you just have to look at it relative to the size of the thing it's interacting with? Like, clearly that's a bulky base, but like, is there a way of just saying it's X amount bulky, therefore we're going to see the less expected result?
Yeah, you calculate like specific
If-
constraints.
Of course, you get handy before you do it.
You would have to get into some molecular modeling,
Okay.
which is really fun. We have a molecular modeling component to OChem Lab. If you feel like hanging out for a while,
Yeah, I know.
doing okay. Yeah. So, short of that, you just have to kind of reverse engineer. Before we had modeling, you'd say based on the degree of hindrance would be reflected in the yield. So, what am I doing? I don't even throw in markers. Oh, nope, this one's still good. So, part of the reason this is 72% is because we have twice the opportunity. If we eliminate here or here, we still get this product.
So you have to look at like all
Yeah, it's like
spots.
all this. Gotta look at all the stuff. This is why OChem is so much fun.
That's pretty cool.
My wife routinely tells me I put FU into fun, like nobody else. And so whenever I say something's fun, everyone goes, yeah, it's gonna be fun, guys. And I'm like, This is neat though, because it's like it's real. It's real. So
But even so,
either I'm making it up. Yeah.
But even so with this one, because with the Zizevs, so yes, it's twice as much opportunity, but even if you have that 36%, it's greater than your 28. So that even excels you.
It's still
depends on
more
the
favored.
Zizev.
Yeah, it's
Yeah.
still more favored. And the reason it's more favored is because to come in and take one of these off is more challenging because bromines are actually pretty large. Methyl group, pretty large. We have this methyl group over here also getting in the way, so you can't come in from the side. If this was CH3, you can come in from the side. It wouldn't be as much in the way. But this group can easily come in here or here and access those positions. So because our base has a hard time accessing this proton, even though this would be a preferred intermediate because of its stabilization of its double bond character, realistically you're just going to you're going to access these positions more readily, and so it's going to be preferred because of the bulky base. So if you're being asked to predict the preferred product a la the last exam for this reaction, and you knew it was specific to the E2 and not the Sn1, or maybe it isn't and you have to predict both, you would go to this because of the bulky base.
So what if it was like, because we said BR is super big, would it
Super big.
would we still have this happening with the CL?
Yes. However, what if it was fluorine?
Yeah, that one.
Ooh.
Yeah, but that one's on the super weak side. Do we have to worry about that then? Okay. Well, I figured yes, but I figured that then doesn't fall into this.
It's like,
Sorry, I mean yes, we worried about it, but I didn't
So-
figure
so-
it falls
so-
into this.
yeah, bromine super big, fluorine Ava size.
It's
It
okay.
keeps its electrons really close to it.
Small but mighty.
Small but mighty. Most electrophilic of all of the students.
It's a compliment.
I feel like that says like low key I'm a klepto, but you know.
Or just super negative.
Right? And you don't want to get burned by it. Because, yeah, it's bad. Hydrofluoric acid burns are bad.
You can do shots
So-
over.
The shots of the forearm, yeah. Yeah, it's character. So,
So you know how to target.
the other exception is, so we have bulky
I'm so
bases
confused
and we
about who
have
I am now.
alkyl fluorides.
Well, thank you for this eventful morning.
It's okay, you're not on camera, so nobody knows who you are on YouTube.
Once I caption it.
Until the picture gets inserted into it. Which, don't worry, the camera on the back is not on. I have to get consent of everybody to do that, and I don't have time to do that. So, because FERPA. So alkyl fluorides are our other exception. So, we've got this nice secondary alkyl fluoride, and what's our base going to be for this one? Methoxide for a base, and that means we can eliminate either from this position A or this position B based on Zaitsev's rule. Because of stabilization of the double bond character, you would expect to eliminate here because you're going to have a more substituted double bond. But what we see is what did I just do? I'll draw it in. One, two, three, four. Okay. Cool. This one is 70%. This one's 30%. So this is a pretty good question. Why? Right? So let's look at the mechanism here and open this up a little bit. So the base comes in, takes the proton, pushes the electrons over here, and would kick off the fluorine. So, why is fluorine not a great leaving group compared to the other halogens? Smaller, so it has a harder time putting those electrons into that same space. So even though it's super electronegative, it likes to hold on to its electrons. It's harder for it to host the extra electrons compared to the larger halogens. It's still a decent leaving group. So it's just not a great leaving group. So the problem is as this double bond starts to form, exceeding the octet, this resists taking those electrons a little bit. And what that does is it starts to push partial negative charge character onto that carbon, forming a carbanion in transition before this is taking those. So you get in this competition, it's like hot potatoes, like, I don't want it, you take it. And carbon's like, I hate electrons, you take it. It's like, no, and so eventually it takes it. But in the meantime, the carbon has to host some partial negative charge. Carbanions have opposite trends in stability versus carbocations. So in carbocations, tertiary is preferred over secondary, is preferred over primary, is preferred over methyl. Why? Are carbocations preferred with higher degree of substitution? Because of the hyperconjugation donating extra electrical density, right? So it's all that extra electrical density coming from the hyperconjugation, which stabilizes that positive charge. Hyperconjugation contributes to electrical density. This already has electrical density as a carbanion. So for carbanion, it's the exact opposite. Methyl, primary, secondary, tertiary. Methyl, most preferred. Primary, second most preferred. So what's going to end up happening is this is going to be preferred because it's going to have less carbanion character in transition state before the fluoride finally gets removed versus this one, because this one has less hyperconjugation. So that's why the fluorine. Now, I'm going to ask you that specifically on the test. No, I won't ask you that. You should know that carbanions, this trend in carbanions, just like you should know this for carbocations. But if you see an elimination reaction happening, an E2 elimination happening with a fluorine, know that is going to go against Zaitsev's rule. So those are two circumstances that you have to be considerate of when you're assessing what kind of product is favored. Yeah?
When you start having like a substitution on one of the other carbons, like not an alkyl thing, but like if you had an oxygen or something else.
What?
Like if you had on the carbon on the left there, like there's the fluorine on the one in the center, what if you had some other substitution on that other carbon? So you end up with.
It depends on the functional group, because we have lots of functional groups which are reactive to bases. So it's entirely dependent on the chemistry of those functional groups. So, yeah, there's no clear answer to that until we get into those functional groups, which will be next chapter. No, not next week, because next week we're going to finish up this chapter. But the one after that, we're going to do alcohols. So everyone's favorite pre-Thanksgiving chapter, and ethers, but less favored. Any other points? Oh, okay. So general reactivities that you need to consider for E2. E2 reactivities, tertiaries favored over secondaries favored over primary because of the degree of substitution generally. So you're going to have faster, more favored reactions if you have a higher degree of substitution in your alkyl halide. Unless you've got a bulky base or an alkyl fluoride. And that is it for E2. Next week we'll pick up with E1 elimination, and then we'll pull it all together into one fantastic thing. So actually before you guys go, this is the chapter that in OChem 1 probably gives people the most fits because it's the most nuanced. So please get in to the extra problems and work the extra problems and try to rationalize. Even though the homework isn't due until next Saturday, get into the problems and start working through these because you want to be comfortable with the scenarios so you start to recognize the patterns faster before the exam. That's all.